Hello students and welcome to this next edition of our physics revision series of class 11 physics. So today we will continue ahead with the topic we were discussing, which is Newton's laws of motion and friction. So in the last session we were discussing about the application of pseudo force in non-inertial frame and also about some constraint relation type of situations. So we will continue with further applications of that today. So let's start with the next example, which is based on the application of pseudo force. So we have this situation that on a frictionless surface, we have a horizontal frictionless surface. We have a triangular wedge, like a triangular prism, which is also having no friction on its surface. So this angle here is theta. So if the angle of the wedge is theta, and this is a smooth surface, as well as this one being a smooth surface. Now, a small block is placed on the wedge. So let's say the mass of the small block is small m and the wedge is of mass capital M. So these values of mass are 1 kilograms and 4 kilograms respectively. And this angle theta is 37 degrees. Now what we are doing is we are pushing this system with an external horizontal force F like this. We're pushing it with an external force F. So you have to find the condition on F, that is how much force you have to apply so that the block does not slip on the wedge. The block remains stationary with respect to the wedge. So the question here is we have to find the magnitude of this horizontal force such that the small block of mass m does not slip with respect to the wedge of greater mass capital M. Okay. And all the surfaces are smooth or frictionless. So first of all, let's understand why this situation is possible over here. So the moment we apply this force on the wedge, what will happen is that the system has a horizontal acceleration A towards the right. So that horizontal acceleration A means that with respect to the wedge's frame, the block will experience a backward pseudo force. And that pseudo force will be pushing the block against the wedge's surface. So if that pseudo force pushing it towards the left is strong enough, then it can balance the weight. Okay, in a certain condition, it can exactly balance the component of the weight down the inclined plane will be balanced by the component of the pseudo force up the inclined plane, and that will prevent the block from slipping. Okay, so let's understand this in terms of two sets of free body diagrams. One, let us understand. So first of all, let us start with the assumption that the condition of the given problem is true. Okay, so assuming small m is stationary with respect to the wedge capital M. Okay. So in that condition, what will happen is that it will look like the system is having a common acceleration. Okay. Under the action of this force. Under the action of this horizontal force, it will look like this whole system has a magnitude of acceleration A, which is common to both the blocks. This is in the ground frame with respect to inertial frame, or in this case, the stationary ground frame. So what will happen here is that as far as the free body diagram of this is concerned, the FBD of the wedge plus the block as a combined body. So on that, there is going to be the external horizontal force, the combined weight, and the normal reaction that the ground is providing. And under the action of these forces, the system has a horizontal acceleration E. So if this condition is satisfied, that the block is stationary with respect to the wedge, then this free body diagram will result in this information. So let us say these are our first two equations. Now, of course, we have to take care of the fact that this condition is correct. So for this condition, we need to understand the free body diagram of the block in the wedges frame and see how it can be in equilibrium. So for the block to be stationary with respect to the wedge, okay, it must be in equilibrium in the wedges frame. So what we mean here is that the wedges frame will be a non-inertial frame. So in that frame, the net force on the block must be 0. So this is the condition we have to solve, that in the non-inertial frame of the wedge, the block's net force, the net force acting on the block must be 0. So let's understand that next. Okay. So we are now in the frame of the wedge. So our reference frame has a horizontal acceleration A, okay, towards the right like this. And in this reference frame, what is happening, that on this block, there will be a total of 3 forces acting, including the pseudo force, the weight of the block acting vertically downwards, and the normal contact force that the surface is applying in this particular direction. So this is the direction tangential to the surface. This is the direction normal to the surface. We can see that this angle will be theta here, as will this angle be theta, because the angle of inclination of the surface is theta. Okay. So this must be in equilibrium in this frame. So net force must be 0. Okay. So the condition for equilibrium you will see here is that mg's sine component has to be balanced by pseudo force's cos component. And of course, this normal reaction, let's write this as n prime, because we have taken the normal reaction with the ground for the whole system as n. So this n prime will be mg cos theta plus ma sin theta. Now the thing is, we just need to understand the acceleration over here so that we can substitute that in our first equation earlier. So we can see here that from this, the condition for equilibrium of the block in the wedges frame, we have from equation number 3 rather, from equation 3 above here, this one, we have that A should be equal to G tan theta. This is a condition that we're getting. This is from equation 3. Okay, as you can see, small m cancels out on both sides. This is the FBD of the block of mass small m. So this is the situation now. So now we will substitute this back in the first equation earlier we had. Okay, so therefore from equation 1 earlier, F is equal to capital M plus small m into A. So that becomes this now. Substitute this here. Get this. So finally our answer becomes like this, that capital F has to be 4 plus 1 kg into G, let's take as 10 meters per second square, into tan 37, which is 3 by 4. So that will become 50 into 3 by 4. That's 37.5 newtons. So this is the amount of force that we need to apply on the system horizontally from the right, so that our given condition is correct. Okay. So I will just leave you with a minute to go through this before we move on. All right, let's move on to the next situation. Now we will again go back to a problem of system of pulleys and constraint relation, but through this example we will understand a second method for constraint relation. We'll understand constraint relations by what is called the virtual work method, or the virtual work done method. So in this, what we'll do is, if we have a system of pulleys, in that the net work done by tension in any inextensible strings is 0. Okay. If the strings in our system are inextensible, then the net work done by tension must be 0. So this is a concept we will apply for the constraint relation. So let's look at this with an example. So suppose we have a system like this now. So we have a system with quite a few number of pulleys. Like in this case, let's say our system consists of 3 pulleys like this. This is a frictionless surface. The pulleys are massless and smooth. So suppose A and B are blocks of equal mass. This surface is also smooth over here. This is a massless and inextensible thread. And A and B are massless, are identical masses. So mass of A is equal to mass of B. So we want to find their accelerations. We want to find the acceleration of A's magnitude and acceleration of B's magnitude. Okay. So in a situation like this, immediately we understand that, okay, the forces acting are like this. There's a uniform magnitude of tension acting everywhere in the thread because it's massless. Okay. And of course, we understand that there is the weight of this block acting downwards on it, the weight of this block acting downwards on it. Some kind of normal reaction that the ground applies on this. It's like this, okay. But what is more important is that we understand this is moving with a horizontal acceleration like this, and this is moving with a vertically downward acceleration. So the first thing we want to determine over here in this problem is the relation between acceleration of A and acceleration of B. So first thing you want to find out is the constraint relation. What is the ratio of the acceleration of A is to B? So as opposed to conservation of thread length, which we had discussed in the previous session, which can also be used over here without too much difficulty, we are going to now apply the concept of virtual work. Okay, so we will determine the constraint relation by using the concept that the net work done by tension T in the thread should be 0. So this is what we call our virtual work theorem. Okay. So if you notice in this particular system, tension is acting in a number of places. So there is tension acting here, tension acting here, tension acting here, tension acting here. Okay. Now after some time, what is happening is, let us say this block is making a displacement from here to here, and this block is making a displacement like this from here to here. Okay. Whereas these are remaining stationary. So you can see that the tension that is acting on the block A and the tension that is acting on the block B, they are doing work. Whereas the other tensions acting on the pulley above or on the ceiling above here, these two are not doing work. So net work done by tension should be 0. So that means work done on the block A by tension plus work done on the block B by tension should be 0. So as you can see here, the work done by tension on block A is plus T into displacement of A. Whereas the work done by tension on block B is the tension force is 3T in the upward direction and the displacement is downwards. So it will be negative of 3T into this. So this relation will hold true at all times. Okay, whatever be the relation, whatever be the value of time, and therefore the displacement of A, the displacement of A and B will have this relation, which means that the displacement of A at any point of time will be equal to 3 times the displacement of B. Okay, so that means that if we differentiate this, we get this, which means that if we differentiate it once more, the second derivative of displacement with respect to time, we get the relation between the accelerations. So this tells us that acceleration of A will be 3 times in magnitude to the acceleration of B at any point of time. So this becomes the constraint relation that we are looking for. The ratio of acceleration of A is to B is coming out to be 3:1. This is a constraint. So this constraint can be demonstrated from thread length conservation also, but it can be more effectively demonstrated by the virtual work method, which I have demonstrated over here. Okay. So just make sure you understand this method carefully once before we proceed ahead. Okay, now once we've got this, the rest is easy. The free body diagrams, we can make them in ground frame only. So for the block A, the forces are tension, weight, and normal reaction. And it has an acceleration which is 3 times the acceleration of B. So we have T is equal to mass into acceleration. And of course, normal reaction balances the weight, which is not really a significant equation. Then for the block B, we have weight acting vertically downwards, same mass as E, but a total of 3T tension acting vertically upwards and as an acceleration like this. So the equation becomes mg minus 3T is equal to m into EB. So this is our fourth equation. So what we will do is from equation 1 above, we will substitute acceleration of A as 3 times acceleration of B. So this equation becomes T is equal to 3 times mass into acceleration of B. And then we will substitute this here. So we have mg minus 3 into 3 times mass into acceleration of B is equal to mass into acceleration of B. So this will now give us that acceleration of B is becoming g by 10, and that is downwards, whereas acceleration of A will be 3 times acceleration of B, which means acceleration of A will have a magnitude of 3g by 10 towards the right. So that becomes our final conclusion. So these are the three equations that we are using: the first equation, the second equation, and the fourth equation. The third equation is not really significant for us over here. Okay, next up, let's look at another version of this type of situation and problem, but with more number of police and little bit more of complication involved. Let's say we have a system like this now, which has a total of 3 police, as you can see, attached to a combination of two blocks. These are police P1, P2, and P3. And these are blocks of mass A and B. So P1, P2, and P3 are massless and smooth police. Okay. All threads are massless and inextensible. Okay. And let's say mass of A is equal to 20 kilograms, whereas mass of B is equal to 10 kilograms. And let's take G as 10 meters per second square. So we want to find the acceleration of A and the acceleration of B. So this kind of a situation is a little bit more complicated in terms of constraint relations. So the virtual work method becomes very important. So the first thing that we need to understand here is that if this string has a tension T1, okay, then our second string over here will have a different value of tension, T2, let's say. Okay. And our third string finally will itself have a different value of tension, T3. So before we get into the virtual work method and all that, to understand how acceleration of A and acceleration of B are related, we need to first understand the relation between T1, T2, and T3. So for that, what we will start with is we will look at the free body diagrams of the 3 pulleys, or actually 2 of the pulleys, only P2 and P3. To understand the relation between the tensions. So if you look at the pulley P3, it has 2 T1 acting downwards on it and T2 acting upwards on it, and it's a massless pulley. So the net force on it must be 0. Therefore, T2 must be equal to 2 T1. That's the first thing we understand. Similarly, if you look at the free body diagram of pulley P3, oh sorry, this one was P3. If we look at the pulley P2, very similarly, we will see that our T3 will become twice of T2. T3 is acting like this, and on either side of the pulley from here, string is pulling it down with double T2. So T3 must be equal to 2 times T2, because this is also massless. So the net force on it must be 0. Okay. So from these equations, what we are getting is that T2 is equal to 2T1 and T3 is equal to 2T2, which is the same thing as 4T1. So suppose my T1 is some T, then T2 is becoming 2T and T3 is becoming 4T. Okay. So coming back to the overall situation, to find the relationship between the accelerations of the two blocks, you will now understand significantly that so now we'll understand in this diagram that on the block A, there is a total tension of T3, which is equal to 4T plus T2, which is equal to 2T plus T1, which is T. Whereas on the block B, there is just a tension of T. And the weight of this block, remember, was 200 newtons. And the weight of this block was, sorry, this one was 10 kg. So this is 100 newtons. And this one was 20 kg. So it is 200 newtons. It was given to us that mass of A is 20 kg. Mass of B is 10 kg. These are the values we had seen. So first of all, what we'll understand from this is that the total tension acting on A is 70 on A. There is a net tension acting upwards, which is 70. Whereas on B, there is a net tension, which is only T. Whereas the weight of A is 2 times the weight of B. So the weight of A is 2 times the weight of B. But net tension acting on A is equal to 7 times T. Whereas the net tension acting on B is T. So therefore, immediately we understand that B has a tendency to accelerate downwards, whereas A has a tendency to accelerate upwards. So this becomes very important for us. Now we know that B is going down and A is going up. So once again, next up, when we want to apply the virtual power theorem, the virtual work theorem, wherein the net work done by tension should be 0 in the system. Okay, so we can see that on the block A, there is a net tension of 70 acting and it is going up. So after some time, if it has a displacement of SA, the 70 will be doing positive work. Whereas if you look at the tensions acting on the pulleys, on pulley P1, there is but it's at rest. If you look at on pulley P2, so net tension is 0 on this because 4T and twice of 2T balance. And similarly, if you look at the pulley P1, T2 is equal to 2T and T1 is equal to T. So again, the net tension is 0. So there's no work done by tension. But on the other hand, if you look at the block B, which is here, there is just tension T acting on it. And B is making a downward displacement. Sometime. Okay, so to apply the condition that the net work done by tension is 0, we will see that the work done by tension on A plus the work done by tension on B, this should be 0 because already on pulleys P1, P2 and P3 the work done is 0. That we have understood. Okay. So on A the work done by tension will be plus 7T into displacement of A, and on B it will be minus T into displacement of B. So the constraint relation that we are getting here is this, that 7 times SA is equal to SP. And double differentiate that, that means that 7 times acceleration of A is equal to acceleration of B. So this is our constraint relation. This will become our third equation. So as you can see, in a problem like this, the conservation of thread length would have become very complicated because we would have to conserve 3 different threads lengths. The thread having tension T1, the thread having tension T2, and the thread having tension T3. These 3 different strings tension, we would have to, these 3 different strings lengths, we would have to conserve them. And that would have made things a bit complicated. But by the virtual work method, we're getting a very easy way to understand the relationship between the accelerations, which is a ratio of 1:7. The acceleration of A is to the acceleration of B is 1:7. Right. So next, all we have to do is write the free body diagram equations and solve them, and that's it. We will get the value of accelerations. Okay. So once you've got this relation between the accelerations, now next up we can see that we just apply the free body diagram equations. So on the block A, there was a net tension of 7 times T acting upwards, whereas its weight was 200 newtons, and it has an upward acceleration now, which we can take as this. Okay. Now similarly, the block B on the other side, it had tension of just T acting, weight of 100 newtons, and it had a downward acceleration of 7 times the acceleration of T. Okay. So for A, we have the equation 7T minus 200 is equal to mass of A into acceleration of A. So we have 7T minus 200 is equal to 20 times acceleration of P. That's our second equation. Whereas for B, we have the equation weight minus tension is mass into acceleration. Now this will become 100 minus T is equal to 10 times AB. That's our third equation. And acceleration of B is equal to 7 times acceleration of A. That was the first constraint relation. Okay. So next up, we will substitute this here. So this equation becomes 100 minus T is equal to 70 times acceleration of A. And then we will substitute T as 100 minus 70 times acceleration of A. We'll substitute this in equation 2. So that equation becomes 7 times T minus 200 is equal to mass into acceleration. Okay. So we have 700 minus 200 is 490 plus 20 times acceleration of E. So acceleration of E will come out to be like this: 500 divided by 510, or 50 by 51, or nearly 1 meters per second square. And acceleration of B will be 7 times the acceleration of A. So that means acceleration of B will become 350 by 51, or nearly 7 meters per second square. Very close to 1 meter per second square. This is very close to 7 meters per second square. So this becomes the final solution. So I will just share the equation solving part with you once you just look at it and understand all the terms. So the first thing we had done actually was to find the relationship between the various tensions, which is over here. Then after that, the next thing was this was the relationship between the tensions. Okay. Then from this we got the net tension acting on A, which was 70, and the net tension acting on B, which was just T. From that we got the virtual work theorem, which gave us the ratio of the accelerations. So this is what told us that the acceleration of B is 7 times the acceleration of E, or E is to B acceleration is 1:7, this relation here. And then finally we put that in the free body diagrams of A and B. So these were the free body diagrams in ground frame or inertial frame. So finally we came up with this solution. Now next up we will see an even more interesting application of this constraint relation method, where we understand something called the virtual power theorem as opposed to virtual work theorem. Virtual power theorem for constraint relations. So in any system with multiple pulleys, and threads, etc., if the threads are massless and inextensible, both the conditions are important. Threads are massless and inextensible, then the net power developed by tension, the net instantaneous power developed by tension within the system must be 0. Just like the net work done in a certain duration by tension is 0. So the net power delivered by tension must be 0. So let's understand this with an example. So why this is advantageous is now because if there is some angles involved, Okay, the threads are at some angles with respect to each other, then this can always be incorporated. Okay, so for example, we have a situation like this now. So we have this situation where this is a massless inextensible thread, and both this and this are massless and smooth pulleys. Okay. Now suppose what is happening here is that the system is released from rest, okay, with the thread taut at theta equal to, let's say, 53 degrees. Mass of A is suppose 5 kilograms and mass of B is 2 kilograms. So you want to find the acceleration of A and B just after the thread is released. And let's say we also want to find out the ratio of their speeds later at an instant when theta becomes, let's say, 60 degrees. Because as A moves, theta will be increasing. So later at some instant when they are well in motion, so VA and VB are both non-zero, because initially they are at rest. VA and VB are zero when theta is 53, but by the time theta becomes 60 degrees, they have some non-zero speeds. So what is the ratio of VAs to VB at that instant? We have to calculate that. Okay. So once again, when we look at this system, the first thing we'll realize is that there is the same magnitude of tension acting everywhere in the thread. So the tension acting on E is going to be a single T at an angle theta to the horizontal, whereas the tension acting on B will be 2T acting vertically. Okay, so that's one important aspect of the question which we will understand. So let me just explain this aspect again. So let's take some arbitrary instant. So the tension in the thread is T like this. Okay. Now at that particular moment, let's say A is having a velocity horizontally like this and B is having a velocity vertically like this. Okay. So we will use the virtual power theorem. that is the net power by tension should be 0. So if you look at the block A, it is moving with a velocity VA like this, whereas the tension's point of application is like this. So this angle is T. Then the power delivered by tension on E, that should be how much? It should be plus TVA cos theta. But similarly, if you look at the block B, the pulley attached to it, there's a net tension of 2T acting vertically on it, whereas B is having a downward velocity of VB. So the power delivered by tension on B, that will become minus 2T into VB. Okay, whereas obviously on this pulley which is hanging on the wall, you can see that the power delivered by tension is 0, because at these points there is no velocity. So at all these 3 points which I'm marking with a cross, tension is not delivering any power. Okay. So the net power delivered by tension will become plus TVA cos theta minus 2T VB, and that should be 0. So we get the relation that at any instant, VA cos theta minus 2 VB should be 0. So this is the constraint relation. Okay. But what we have to understand here is that in this constraint relation, VA, VB, and theta, all 3 quantities are instantaneous. That is, they are variables of time. Okay. So that makes things a bit tricky, but luckily, because we are calculating the acceleration just when the system is released from rest, it will not be difficult for us. Okay. So this is the constraint relation between the velocities. So now to get the constraint relation between the accelerations. Okay, so next up, for the relation between acceleration of A and acceleration of B, we will just differentiate this. Or let's just first write it like this only. Should be 0. So differentiation of VA cos theta should become 2 times differentiation of VB. So in general, this is complicated because remember theta and VA are both variables. Okay. So it is like this. So instantaneous acceleration of A into cos theta plus VA into minus sine theta d theta by dt is equal to 2 times acceleration of B. So this is the general constraint relation. This is the constraint for acceleration of A and acceleration B relation. Okay. However, here what is happening is that at t equal to 0, after the system is just released, so at that moment the instantaneous value of VA and VB is 0, and the instantaneous value of theta is 53 degrees. So we substitute that here. So substitute this information in the constraint relation. and that gives us something easier. Just because VA happens to be 0 at that moment, we are getting acceleration of V into cos 53 degrees should be equal to 2 times acceleration of V. This relation. This will not be true later when VA is not 0, but at that particular moment when the system is starting from rest, because the instantaneous value of VA is 0 and the instantaneous value of theta is 53, this will be the relation between the accelerations. Okay. So this is just after release. This just after the system is released, only at that moment. So now let's take this as our first equation, therefore. This is equation 1 for us, okay. And let us look at the free body diagrams. This we have taken as 5 kg, so that's 50 newtons. It's having some acceleration like this. And the other one, 2t upwards, and its weight is 20 newtons and is having a downward acceleration of EB. So our equations now become so 3 by 5 T is equal to mass of A, which was 5 kg, into acceleration of A. So that becomes our second equation. This was our first equation. Okay. And for B, we have weight minus 2T is mass into acceleration. So we have 20 minus 2T is equal to 2 times E. So that becomes our third equation. Okay. And now we will be just solving this system of equations. Okay. So what we can do is this equation becomes 10 minus T is equal to EB by dividing by 2. Then substitute this here. So this becomes 10 minus 25 by 3. And then we can substitute this over here. So so this becomes the acceleration of A, and then the acceleration of B is as you can see, the acceleration of B is 3/10 of the acceleration of A. So we will get these kind of instantaneous accelerations. Okay. As far as the second part of the question is concerned, at a later instant when the angle of the thread becomes 60 degrees, at that kind of an instant, the relationship between the velocities we want to find out. So when this angle has become 60 degrees, at that moment, if this is moving with VA and this is moving with VB, so you can see that we just have to rely on that constraint relation that we saw earlier. So TVA cos 60 minus 2TVB should be 0. So like this. So this is the second part. We wanted to find out VA is to VB at an instant when theta is equal to 60 degrees. So this is the answer to that. Okay, so this is the more complicated example of constraint relations when there is some kind of an angle involved like this. Okay. Now next we will move on to an example where there is a situation of tension in a heavy rope, and we have to understand how to deal with that. So let's start with a simple situation. We are using a heavy chain or rope kind of thing to suspend a block vertically. So this is a uniform heavy rope. So by uniform, what we mean is that it has a uniform mass per unit length. It has uniform thickness and density. So which means that it has a uniform linear distribution of mass. The mass of the rope is uniformly distributed over its length. So its length is L and mass is smaller. Okay, and this is a block which is of mass capital M. So now if we have a point over here in the rope which is at a distance of x from the bottom end, we have to find the tension at that point as a function of x. So find the tension T at a point P in the rope. So let's understand this. So what we'll do here is, first of all, we'll make the free body diagram of the block. Okay. So if the tension at the bottom end of the rope is T1, this block is at rest. So T1 is equal to mg. So this is the tension at the lowest point on the rope. Okay. Now if we make a free body diagram of the rope itself, the heavy rope, then in that free body diagram we can understand that the tension at the bottom end is capital Mg, which we just calculated. Suppose the tension at the top end is T2. The rope's own weight is small mg and the rope is at rest. So T2 is equal to T1 plus mg. So T2 is equal to m plus mg. So this is the tension at the topmost point. On the rope. So you can see that T2 is greater than T1. See from this and this. It's very apparently clear that T2 is greater than T1. In fact, T2 is equal to T1 plus the weight of the rope. Okay. Now to find the tension at that point P, what we will do is we'll make a free body diagram of a section of the rope. Okay. So to find the tension at P, we make a free body diagram of the section of length x from the bottom, okay, of that rope. So this is that point P. Okay, this length is x. So at the bottom the tension acting is T1, and at this point the tension acting is TP. Suppose we want to calculate that. Okay, and of course the weight of this section of the rope, we'll write it as mxg, where mx is the mass of a section of length x. Okay, so mass of that section of length x will become mass per unit length into the sectional length. Okay. So we have, since this is also at rest, we have tension at the point P will become T1 plus this. So tension at the point P will become T1, remember, was capital Mg plus this quantity. So overall we can see that it's going to be this sort of a linear function. So because the distribution of mass is uniform, so the tension is going to vary uniformly or at a linear rate. Okay, so we can also understand that if we look at the relationship between tension at the bottommost point and tension at the highest point, so we are looking at tension as a function of x, suppose. So we will see that that relation is going to be a linear function which varies from a value equal to the weight of the block to a value equal to the total weight. So this graph also conveys the same information that we are getting from this relation, that it varies linearly with respect to the position. Okay. I'm just expanding this a little so that you can understand the relation between the graph and the equation that we've developed here. Okay, let's understand another example involving variable tension in a heavy rope. So this time we'll see a situation where there is a horizontally accelerated system under the action of this kind of heavy rope and tension in it. So let's say we have a frictionless smooth surface, and on that we have placed combination of two blocks placed like this. Okay. And further the blocks are joined by a heavy rope. So like this. Okay. So the heavy rope is sort of, its weight is supported by the floor. Okay, because after all we have to consider the fact that it's a heavy rope. So now this whole thing is being pulled with some horizontal force F like this, and this is a heavy rope which is again uniform in terms of its distribution of mass, etc. Okay. So now the given information is that the rope has a mass of, let us say, 2 kilograms and a length of 10 meters, and A has a mass of 18 kilograms and B has a mass of 30 kilograms, and F, the force we are applying horizontally, is, let us say, 15 newtons. So first of all, find the acceleration of the system. Then secondly, we will also find the tension at the ends of the rope. And finally, we will find something very specific over here. We will find the tension at a point. See, the mass of the length of the rope is given as 10 meters. So we will find the tension at a point at x equal to, let us say, 3 meters from the left hand side end of the rope. So we will find the tension at that particular point. Okay. So just give this question a try for a moment. We will discuss. Okay, so let's understand the application of this very simple problem. So what we will do here, the easiest way to solve the entire problem, just come to it straight away without. So first we will make a free body diagram for the block A plus the block B plus the rope as a combined mass. Okay. So that mass is mass of A plus mass of B plus the mass of the rope. So that is 18 plus 30 plus 2. So that I believe is 50 kgs. Okay. So for that 50 kg combined mass, which you can see from the data given here. Okay. What is happening is we are applying a 50 Newton force. So on that combined mass, we are applying a horizontal external force of 50 newtons, and the combined weight is balanced by the combined normal reaction. So N is equal to normal reaction on E plus normal reaction on B plus normal reaction on the rope. It is the combined value of normal reaction by the floor on that system. Okay. So this system now has some acceleration E, which we want to find out. So F should be equal to, very simple, we don't have to do anything much here. So it should be equal to the combined mass into the acceleration. So from this equation, we will get 50 newtons is equal to 50 kgs into E, or the acceleration of the system is 1 meter per second square. So this is the first thing. Now, once we have found out the acceleration of the system, now we are in a position to calculate everything else very easily. So for example, if we make the free body diagram of the block E, we'll understand the tension acting at this end will give this the acceleration of 1 meter per second square. So tension at this end of the rope will become 18 newtons, because mass of E was 18 kilograms and the acceleration was 1 meter per second square. Okay. Now if we make the free body diagram of the block B, so for that we can understand we are applying the force of 50 newtons from this side, and we have the tension that the rope is applying something from this side unknown. Okay. Weight of the block B, normal reaction on B, but again this is having an acceleration of 1 meter per second square. So we have F minus tension at this end of the rope is equal to mass of B into acceleration. So 50 minus this tension is 30 into 1, because mass of B was 30 kilograms. So you can see that the tension at this end of the rope is 20 newtons. So now we have understood one thing, that as far as the rope is concerned, okay, the tension at the two ends are like this. So now when we consider any point within the rope which is, let's say, at a distance x, what we can do is we can make the free body diagram of that section of the rope where this distance is x. Okay. And we can see that okay, so we'll have this relation that tension at the point P minus tension at A is mass of that section of the rope into E. So mass of that section of the rope will become M by L into X. So tension at the point P will become TA plus m by L into x into A. You'll see that tension at this point in general will become 18 plus, now mass of the rope was 2 kgs, A was 1. So, and the length we had taken to be 10 meters. Like this. So tension at the point P will be 18 plus 0.2x in newtons, where x is in meters because you're taking 10 in meters. Okay. So for example, at x equal to 3 meters, we can see that the tension will become 18 plus 0.6 or 18.6 newtons. Okay. So any arbitrary point we can find out like this, but more importantly, we once again know that the relationship between tension and position will be linear, as you can see from here. So it varies between 18 and 20 newtons. So this is the analysis in this kind of a situation of variable tension in a heavy rope. Okay. So with this, we complete this session today, people. And next time we will start with our analysis of problems with friction or with rough surfaces, and we will understand the concept of limiting static friction and kinetic friction, and etc. etc. So important lecture today because we've seen the constraint relation for multiple pulley systems with two distinct methods, which is the virtual work and virtual power method. Both are very similar, but they have their own advantages over the thread length conservation. And we've also seen an example of pseudo force concept being applied. So that was also very important. So make sure you revise these examples carefully and you're prepared for the next lecture with some basic revision about friction. So wish you all the best. That's it for today.